Hey guys, today I want to present a solution to the Belarus Team Selection Test 2016 problem 3. At first, let's have a look on the problem statement. We are asked to find all prime pairs PQ such that the following equation, p to the power of 3 minus q to the power of 3 is equal to pq to the power of 3 minus 1 holds. The first thing we want to do is to rearrange this equation in such a way that we can factor both sides. So this equation here is equivalent to p to the power of 3 plus 1 is equal to pq to the power of 3 plus q to the power of 3. The left hand side can now be factored as p plus 1 times p squared minus p plus 1. And on the right hand side we can factor out a q to the power of 3. So the right hand side is equal to q to the power of 3 times p plus 1. Now we see that we have a factor of p plus 1 on both sides, and since we work with prime numbers p and q, we can divide both sides by p plus 1 because p plus 1 can't be 0. So we get that this is equivalent to p squared minus p plus 1 is equal to q to the power of 3. Now we want to try again to factor this equation, and therefore we bring the 1 to the right hand side because then we can factor the p on the left hand side and can also factor the right hand side. So this is equivalent to p squared minus p is equal to q to the power of 3 minus 1. And now we can factor both sides and get that this is equivalent to p times p minus 1 is equal to q minus 1 times q squared plus q plus 1. Now we know that p is a prime number and therefore p must divide one of these two factors. So the first case is that p divides q minus 1, but this directly implies that p is less than or equal to q minus 1, which is less than q. If we have a look back onto our equation here, we see that if p is less than q, then p to the power of 3 is clearly less than q to the power of 3. So the left hand side is negative and the right hand side is clearly not negative. Therefore, this case here is impossible and we get a contradiction. So we get that p must divide q squared plus q plus 1. Now the information that p divides q squared plus q plus 1 is very useful because at first we can write that this equation here is equivalent to p minus 1 over q minus 1 is equal to q squared plus q plus 1 all over p. And now, since p divides q squared plus q plus 1, we know that this is an integer, therefore this must also be an integer, and we get that q minus 1 divides p minus 1. Therefore, we get that there exists some k from the natural numbers such that k times q minus 1 is p minus 1, so k times q minus 1 is equal to p minus 1. Now we can use this identity here a second time because we have a formula to calculate p in terms of q, and then we have the term q here on the left hand side and also on the right hand side, which is really nice. Therefore, at first solve this equation here for p, we get that p is equal to kq minus k plus 1, and now we plug in this into the divisibility equation here and get that kq minus k plus 1 must divide q squared plus q plus 1. Now a normal approach in such situations is to get the right hand side as small as possible, and therefore it's maybe sometimes a good idea to multiply the right hand side with some factor in order to then subtract a multiple of the left hand side and get a small value. So from this equation here we get that kq minus k plus 1 divides k times the right hand side, which is equal to k times q squared plus q plus 1. Now if the left hand side divides the right hand side, we can also subtract a factor of the left hand side from the right hand side, and the divisibility condition stays the same. Therefore, we can write here a minus some factor times kq minus k plus 1. And if we have a look which factor is our best choice, then we see that here our biggest term is kq squared, and in order to get this term cancelled out, we want to take the factor q here. Now we can evaluate the right hand side and get that our first product is equal to kq squared plus kq plus k, and our second factor is minus q squared k plus qk minus q. Now we indeed see that the kq squared term cancels out, and we end up with 2 times kq, so it's equal to 2 times kq plus k minus q. From this equation we see now that on both sides kq is the biggest term, and on the right hand side we have 2 times kq, and on the left hand side 1 times kq. Therefore we might guess that the right hand side is 2 times the left hand side. And now I will prove correctly that this is indeed the only possible case. From this divisibility condition we now know that there exists some a from the natural numbers such that a times the left hand side, so a times kq minus k plus 1 is equal to the right hand side, so this is equal to 2kq plus k minus q. As I already said, we want to come up in the end with the result that a is equal to 2, so for a contradiction in the other cases, assume at first that a is less than or equal to 1. Here we can now write that 2kq plus k minus q is equal to a times kq minus k plus 1, and now we can bound the right hand side by the fact that a is less than or equal to 1, so this is less than or equal to kq minus k plus 1. This less than or equal sign is only true because our second factor here, kq minus k plus 1, is always positive since kq is greater than k. Here I want to mention that since we have k times q minus 1 is equal to p minus 1, and both p minus 1 and q minus 1 are positive since p and q are primes, we know that k is at least 1. From this we can bound the left hand side, namely we can say that this is greater than or equal to kq plus k, since we have here 2k minus 1 times q, and 2k minus 1 is greater than or equal to k. Now we see that on the left hand side we have a kq plus k, and on the right hand side we have kq minus k plus 1, but we also know that k is at least 1, and therefore it is impossible that the right hand side is greater than or equal to the left hand side, and therefore this is a contradiction. The second case we want to consider now is that a is greater than 2, so we have that a greater than or equal to 3. And here we use the same idea than in our first case, but this time we bound exactly our equation the other way around, so we get that 2kq plus k minus q, which is again a times kq minus k plus 1, is this time greater than or equal to 3 times kq minus k plus 1, and this is equal to 3kq minus 3k plus 3. Now we can bring the 2kq to the right hand side and all the other stuff to the left hand side and get that 4 times k minus q minus 3 is greater than or equal to kq. Here we directly see that if q is greater than or equal to 4, this is a contradiction because we have here 4k and then we have here at least 4k, and this term here is negative. Therefore we get that q is equal to 2 or q is equal to 3. Here we see that if we plug in q equals 2 in this equation, we get 2 minus 1, which is equal to 1, times q squared plus q plus 1, which is equal to 4 plus 2 plus 1, which is 7. So we have p times p minus 1 is equal to 7, so is equal to 7, and this equation has no solution for p. On the other hand, if q is equal to 3, we get 3 minus 1 as this factor, so this factor is equal to 2, and on the other side we get 3 squared, which is 9, plus 3 plus 1, which is 13. So our second case is that p times p minus 1 is equal to 2 times 13, and this case is also impossible. Therefore, in the case that a is greater than or equal to 3, we get also a contradiction. This means that our only possible case which is left is indeed that a is equal to 2, and on this case we have a look now. So now we are in our third case, and here we have a equals 2, so we can plug in a equals 2 into this equation here and get that 2 times kq minus 2k plus 2 is equal to 2kq plus k minus q. Here we see that the term 2 times kq cancels out, and then we can bring the minus 2k to the right hand side and the minus q to the left hand side and conclude that q plus 2 is equal to 3k, and this is equivalent to k is equal to q plus 2 over 3. Now we remember this equation here, how we define k, namely that k times q minus 1 is equal to p minus 1, and therefore we can plug in k for this k here and get that q plus 2 times q minus 1 all over 3 is equal to p minus 1. And here we can also bring the minus 1 to the left hand side to evaluate p, and so we get that p is equal to q times q, which is q squared. Then we have a 2q minus q, so plus q, and then we have a minus 2, but since we bring the 1 to the left hand side we got a plus 3, so we have here a plus 1 all over 3. Now we remember this equation here, namely that p times p minus 1 is equal to q minus 1 times q squared plus q plus 1, and since we evaluated p minus 1 and p, we can plug in these two values in the equation there and get that q minus 1 times q squared plus q plus 1 is equal to p, so q squared plus q plus 1 over 3 times p minus 1, and this is equal to q plus 2 times q minus 1 also over 3. Here we see that the factor q minus 1 is on the left hand side and also on the right hand side, and additionally also the factor q squared plus q plus 1 is on the left hand side and on the right hand side. So we can divide these two factors out because these two factors are clearly not zero since q is a prime, and then we can bring the 3 times 3 to the left hand side and conclude that 9 is equal to q plus 2. This immediately tells us that q is equal to 7 is the only possible solution. Now we have to evaluate p, and therefore we use this equation here, namely that p is equal to q squared plus q plus 1 over 3. So we get that p is equal to 7 squared, which is 49, plus 7 plus 1 over 3. And here we see that this is equal to 57 over 3 is then equal to 19. Now we figured out that q equals 7 and p equals 19 is the only possible solution. And now we can plug in these two values into the equation here, which is equivalent to our equation from the beginning. And then we see that this is indeed a solution, and therefore we have exactly one solution to our problem. And therefore we are done.